So where we ended yesterday was with this equation. We had just done a basic calculation for Brownian motion, which is just a way of getting randomness. And so we said that this is going to be our model for stock price. Where and I think I did this also yesterday, so this is repeating myself. So x0 is the initial price. Sigma squared is the variation parameter, or sigma is, whichever way you want. Which is a measure of volatility. U is the drift parameter, which is a mix of inflation and the fact that stock tends to go up faster than the economy in general. Oh, and then the whole thing that we did to set this up. The B of t is Brownian motion, so that this won't just go up, but it'll go up and down randomly. And the little thing is, as always, the mean of the Brownian motion is 0. But now we're assuming the variance is t as opposed to the sigma squared t that we did yesterday, on Monday. And that pretty much is just, if you look at the original equation, we took out the sigma, so we're just kind of emphasizing the sigma because that's something we can calculate. So both the sigma and the mu are things that we could get estimates for using historical data. So this is where we ended yesterday, I think. And so what I was going to start today with is just, now let's actually use it to talk about the probability of something. Oh, there we go. So let me ask, can anyone hear me? Okay. So I guess, I guess so. So again, let me know if it comes out. So we got to hear yes on Monday, but did we do an example with this? I don't think so, but did we? I set up the notes. The notes I did the example, but I don't think we got to it. Is that true? Okay. So, and for this, remember what we're assuming to be able to use the Brownian motion. We are assuming that the percentage change in the stock is a fixed distribution, and the change one day is independent of the change the next day. So we're assuming independence, and we're assuming that there's one distribution that gives you the different percentage changes. So now let's use it. And you'll see this sort of gets some of the calculation that we had for the previous one. And might as well make it really basic one so the numbers turn out somewhat nice. Since I'm not in finance, I have no idea if these numbers make sense or not. So I don't know if sigma is, if that's especially big or it's small or whatever. So I'm just making up numbers here. So we assume the price of stock currently is $100 with a drift parameter of 0.05 and a sigma of 0.8. And I want to find what's the probability that the price in, say, 5 years is more than $175. So we put everything into our model. So you can see we have the x0 is 100, sigma is 0.8, t is 5, so plug it in the model. At this point we have two options. One is we could solve for the new distribution, which is we have the original distribution b of t is normal with a mean of 0 and a standard variance of t, and we can then get what is the distribution for this thing. But we don't really use it enough, so what we're going to do, I'm going to make you do, is do the algebra to get this in terms of b of 5, which we know. So we're going to do the algebra to solve for b of 5 in terms of the number. So divide both sides by the 100. And I forget if we've done this in this class or not. How do I get rid of the e? Yeah, take natural log both sides. And then subtract the 0.25 and divide by the 0.8. Get that number. And as always, you're checking my arithmetic, I get that. And now that we have it in terms of b5, we can use the fact that b of 5 is a normal distribution with a mean of 0 and a variance which is equal to t, which in this case is 5. And so as with Monday, we can either now standardize the number and then use a table to get the probability, or use calculator. And remember, we want to go above the 0.39 to infinity, but we can't put an infinity, so just put a large number there. I get something like that. And that's second number, not that it matters much, it's a 3. And we can also just throw this into an Excel sheet or something like that and let it go to see what happens to the price, see what it looks like, see if it looks realistic. Obviously, we're not going to do it here. So any questions on this? All right, so what we want to do with this, so a little thing is, I'm not doing, since I'm writing the notes before and I'm not following my notes exactly. So give me a second. So in the notes, I also do a couple basic Brownian motion examples. So if you go online to the notes under course material, you can see those, and you'll let me know tomorrow if you want to see them. So here, if you looked at the previous one, in this setting, the variance is just t. In the previous setting, so for Monday, we had that the variance of b of t is sigma squared times t. But because we wanted to emphasize the sigma, we pulled that out of the b. So that's what this is, this 0.8. And made it simpler. The variance of b of t is t. And remember, we could do that because Brownian motion came out of a random walk, and we had two things that were letting go to infinity, letting go to zero, the time between steps and how far we move for each step. So therefore, we can control what type of numbers we get. So it's always going to have to involve t, but we can make the number in front of it a sigma squared equal to a 1. So if it's just Brownian motion, I might give you a sigma, in which case variance is sigma squared t. In terms of the stock price, the variance will always just be t. So any other questions with this? What I'm going to try to do today is, this by itself is just the model. As I said, you can look at, see how realistic you think it is, but we want to get something out of it. So I'm going to skip more examples here. We'll fill those in tomorrow. So we'll do examples of Brownian motion and this type of thing, this stock again. But let's figure out what we want to do with this, which is what we really want to get to do is, if we're using this model for the stock price, what should we be charging for a stock option? So, is that better? Yes? Okay, good. So what we want to do is, we want to do kind of the same thing we did with the basic stock, which is we want to set the two equations, expected value equations equal to 0, and then solve for the price that we should charge for stock, for options. Before we do that, we have to add a couple little definitions, because now we have time. So we have what's called present value and future value. And the idea behind this is that money that you have right now is worth more than money you would have in the future. So if I want to compare the price of stock now to the price of stock in 10 years, I have to equalize that. So if I take the price of stock at time t and multiply by e to the negative at, that is called the present value. So it is worth what it is worth if we were given the money now. And of course, we can go the other way. The future value of current stock price is multiply the current stock price by, again, the e to the at. Given the idea that money now is worth more than money that if you got the same amount in 2 years. Because we're doing normal things with the normal distribution, we know we're going to want the expected value. So a little lemma, which I will, as usual, kind of partially prove. Is given by this. So this we'll use in a bit. Sort of as you might expect, because for the arbitrage theorem, we want the expected values for a given probability distribution to be something, so we expected value. But we'll use that in a second. And that's a e to the 1/2 sigma squared t plus mu t. So partial proof. It's all right at the end of this sort of proof. So let's find e of e to the az. You can see this is sort of similar to what we want because we know that Brownian motion is normal. It isn't quite standard normal, but we'd be able to deal with that. And we don't have the plus mu t, but that's just a constant which we can pull out, so we can deal with that easily also. So where z is the standard normal. And we know the way you do any expected value is you multiply that function times the probability function, which in this case is the standard normal. So that's a 1 over square root of 2 pi e to the negative 1/2 z squared, and that's supposed to be a dz. And going back to the beginning of the course, you can probably guess how we do this because we don't want to try to do the antiderivative because the e to the negative 1/2 z squared doesn't have an antiderivative. So what we want to do is manipulate this so it is a different normal distribution. So we can pretend that part of it as an integral of 1. So let me combine the sum of pieces. So bring the exponents together. I win the exponent. I know the general thing is is that, or if you can't see it, I'll bring it down here, is the 1 over sigma squared of 2 pi e to the negative 1/2 in parentheses x minus mu over sigma quantity squared. So I want to bring the negative 1/2 out. Which gives that. That's a z squared still. And since we want it in the form of something squared, I want to complete the square, which you might remember from the beginning. And remember that to complete the square, what we do is we want to add the middle coefficient divided by 2 squared. So the middle coefficient is negative 2a. So therefore, we're going to add 2a divided by 2 squared. But of course, I can't just add it. I have to then subtract it, but that's minus 1/2, so I'm going to do plus 1/2 a squared. So that way I haven't changed anything. But now what's in the parentheses is now a square. And I will want to separate this. And notice this doesn't have the variable in it, so that's a constant, so I can pull it outside. And notice this is similar to what I have up here if I'm letting mu be a and sigma be 1, which means it's a normal distribution, which means its integral from negative infinity to infinity is 1. So therefore, this comes out to e to the 1/2 a squared. And let me just rewrite, goes to dot dot dot, putting in the details. That e of x of t is this. And as I said, this we're going to want because the arbitrage theorem, we're setting expected values equal to 0 and so on. So we're going to expect the value. But this, what's in the box at the bottom, is what we really want. So this is all kind of just the details, but any questions on this? Give you a minute to write. Although this is in the notes that I put up on Blackboard, so it is also written out there. Okay, so any questions on this? Okay. So now we want to introduce the option. So now what we want to do is say, well, how much should I charge for an option if the option will allow us to buy the stock for K dollars, no matter what its actual price is, in T years. A little thing, there are different types of options. In a general way, there is what's called a European option and what's called an American option. In the European option, if I have an option set up like I do here, the only time you can buy it is at the end of the T years. Whereas for the American option, if it's set up the same way, you can buy it any time up until, and I'm going to write this later, up until T years. So if you have an option to buy in 3 years, you can buy it 2 days later, a year and a half later, anytime up to that 3-year. Whereas for the European, you can only buy it at the 3rd year. And this is going to be calculation for the European option because obviously that's the easier one because it's at one set time. So again, similar to what we did with the basic sub, we notice that, well, there are 2 cases for the value of how much we're going to make from the option, depending on what the price of the option is. And that should be a capital T. So first, if the price of the stock at time T is less than K, how much can we make from the option? Or how much do we make from the option? Nothing, right? It's worthless. And the equal, of course, you can put in whichever one you want. If the price of the stock is bigger than K, then you will buy it at K and then sell it for whatever the price is. And so in that case, it's the difference. Just because I don't want to write this 2-part thing, let me call this as a shorthand this, x of t minus k plus, which is 0 if x of t minus k is negative, and the value as it is if it's positive. So this would be its value at time t, but we're paying for the option now, so we need to know what's the present value. So as with the definition, we're multiplied by e to negative at. And again, I'm mixing the thing that this should be a capital T again, where a is the inflation rate. So that's the value, the current value of the option if it goes up. Oops. And according to the arbitrage theorem, we need to be on a probability distribution so that the expected value of this thing, the value, minus the c is equal to 0. So we get one of our 2 equations. This is for the options, which we'll have to deal with in a second. And I'm going to rewrite this, so this isn't quite the end yet because we have to deal with the E of P. Okay. So options, so now we have to do stock. So any questions on this? We need the same thing for stock. We need the difference between what it is now and what it is in the future to be the same on average. So we need that. And again, I'm mixing my t's. That the expected value of the price of the stock at time t is equal to the future value of the current price. And we know from the lemma that in general, the expected value of that is given by that. So we get an equation for the stock. So again, we set something equal to 0 here. I'm bringing one thing to the other side. And we have our two equations, sort of. Let me underline this twice because this is one we're going to keep. Sorry about that. So here I'm just saying, well, what is x of t? So using the same equation, get that. We know that and again, I'm mixing my t, sorry. We know that b of t is normal with a mean of 0 and a standard deviation of square t. Therefore, sigma b of t plus mu of t, mu times t, has a mean of mu times t. And it has a variance of sigma squared t. Since I don't want to write this thing too often, let me let that be y. So c, which is the expected value of that, well, b of t is normal, so we're going to do the same thing. We're going to multiply this thing. And I lost a negative here because present value. we get that. This part is the fact that it is normal. The reason we're subtracting doing y minus mu t is because the mean is mu t. And since the variance is sigma squared t, we have that in the two places. So this is our second equation. So as usual, we get two equations that we want to solve for. One for the stock, the one at the top, and one for the options, the one at the bottom. And here it gets tedious. It's not necessarily difficult. So for example, to get rid of this plus, which we can't really deal with, we'd say, well, if x0 to the y is bigger than k, it's going to be just the value as it is. If it's less than, it's going to be 0, which is going to fall off. And so what that's going to mean is we're going to replace the negative infinity by where x0 e to the y becomes k. So we would replace that limit with that. Once we do, the rest of it, we're going to do what we did in my quick lemma before, which is I would want to bring the two exponentials together, complete the square to make it normal, so that part of it can be something where we know the integral, and just keep going around. And then this top one here is a fairly easy one. You can pretty easily see that the x0 is going to cancel. We can take the natural log of both sides, and we need a times t equals this. The t's cancel, so you can see that a would have to be 1/2 sigma squared plus mu. So it's not necessarily a difficult system of equations to solve. It's just really tedious. So what I'm going to do now is go straight to the actual solution. So any questions on the setup? So we get this two-part thing. Where, let me remind you all the little pieces. So here x0 is just the initial stock price. Again. The sigma is, or sigma squared, whichever way we want to write it. Let's say the variance parameter k is equal to price can buy with the option. Capital T is when you can buy with the option. A is equal to the inflation rate. And this I took from where I got some of this stuff. So you can either leave it like this, or this is just the CDF, or the standard normal distribution. So some ways you could also write this as, if you rather make it explicit, like that. As I said near the beginning, so this is the solution for Black-Scholes equation to figure out what we should charge for options. And as you can tell, we're doing a very simplistic one. If you're doing the full one, instead of having just these two equations for expected values, you'd instead get partial differential equation. And to get the solution, we'd have to solve the partial differential equation. So we're doing just kind of a simple version of it. But if you look at it, in the first couple examples we did, where we didn't involve time, we didn't have inflation, well, for 2 choices, it was pretty easy. But for 3 choices, it was kind of a pain. Whereas this actually isn't bad. It's a messy equation, but all you're doing is plugging stuff in. So this again is in my notes, so if you don't have it, you can write it down then. But so any questions on this, on what's going on, before we do an example? Show what we're using it for. Okay. So example. The current price of a stock is $30, which we assume natural way the capital is by geometric Brownian motion. It's a finance economics equation. If that is realistic or not, I don't know. Assume the drift parameter is 0.1. And assume the variance parameter is 0.01, or sigma is 0.1. As with the example where we got the probability of the stock moving, I have no idea if those numbers make sense or not. I would assume mu isn't too bad, because if the inflation rate is 1%, that's relatively close to where we are now. So it would probably be a bit more than that, but as I said, I don't know if those are good numbers. If we're going to sell an option to buy the stock for $32 in 2 years, then how much should we charge? So this is the question we want to be able to answer. And from the previous one, we know if we charge the wrong amount, that there will be arbitrage and things are going to go badly. Because that would mean that there's a bet that is guaranteed to make money where you buy some stock, you sell some options, and if you do it correctly, you're guaranteed to make money. So looking at the equation from before, we have all the things we need. We have x0 is equal to, we have k is equal to 32. We have the a is equal to 0.02. Sigma is equal to 0.1. So we have all those. A little thing, which I've been told about, but I'm not sure I completely believe, is there is something little going on. And this comes up somewhere else, which is I give you a drift parameter, but if you look at the solution for the option price, mu doesn't come up. So the drift parameter, even though it's part of what we use to get the stock price, included in the solution. So I include it, but we don't really need it. This is what we're trying to do. And pretty much with our solution, we're just plugging in. So it's a two-part piece. So B is equal to natural log of x0 divided by k plus a minus sigma squared over 2 times capital T, and then divided by sigma times square root of t, again, capital T. You get that as a number. By itself, it doesn't really mean anything. It's just so we don't have a huge long one-part calculation because we'd have to put this wherever we see B in the next part. As always, you will double check my numbers, so I get that. And the formula for this is 30 times, this will be the CDF for standard normal, against the sigma squared of t plus b minus the k e to negative a times capital T, and then v of b. So let me remind you what we're getting here. So this I get is using calculator is this, the CDF for Z. Z has a mean of 0 and a standard deviation of 1. So depending on which calculator you have, you can either put it in like this, because if you leave off the last two numbers, it assumes it's C. You have the one like mine where if you pop up, then you'll put in that the mean is 0 and standard deviation is 1. Do the same thing for the phi of B. Plug it all in. and you get a price that you charge for the option. And here, as you might expect, you can't charge too much for it because since mu and sigma are fairly low, it's not changing much. So obviously we have to do another example, but in some ways you can see this pretty much is a straightforward thing. There's not really a calculation. As long as you know the solution in that two-part form, all you're doing is pulling in numbers. It's a bit tedious, but you get back one answer. And for a while at least, this solution was actually being used to figure out what you should charge for options, where you would use past data to figure out what sigma is, and then plug it in. The formulas have been updated several times, so I'm not sure how close this would be. But any questions? Okay, so just a few notes. As I said, this is for what's called a European option, which is if we have an option to buy it at time t, we can only buy it at that one time. Whereas an American option would allow us to buy it at any time less than or equal to that time t. So the American gives us a deadline. And so for that one, obviously, we'd have to do some kind of integral sum. So obviously, that would make it more complicated. So pretty much that's it. I said we have to do more examples. A couple little things. Is if you go back to our original equation for the stock price, you get this kind of weird thing, which is if I let the drift be zero, if the drift is zero, you kind of expect it to just stay about the same. But here it's still going to increase on average. And the solution for C doesn't include the drift parameter. And the way that last one's been explained to me, which I'm probably going to mess up, is that if a stock is increasing faster than it should, so increasing faster than the general thing, then people are going to start selling, which will drag the price down. If it's growing slower, it will tend to push it up because people will start buying it. And therefore, everything, all the different stocks on average are going to tend towards the general drift parameter. And so therefore, since everything tends to the drift parameter, it just kind of falls off. So that becomes our new middle. And we're looking at how high or low, how high above or how low below it is. As I said, I'm not very knowledgeable about the finance. So let me stop here. Before I go, and before I ask you more questions, this is the reminder that the second test is a week from tomorrow or Friday. So in a day or two, I'll put out something, or you'll just email me telling me that you want to take it Friday instead of Thursday. So the general one will be on Thursday, roughly at class time. If you can't make it, or at this point, why not? Don't want to take it on Thursday, then at some point we'll talk and I'll set up a second time on Friday. So if you want to take it on Friday, at some point you're going to email me either after I send out something, or you can just email me now, and you're going to give me possible times you can take it. Try to consolidate it at least somewhat. And I will put out a review by the end of the week. Next Wednesday we'll do nothing new, which means the last day we do anything new, because after next week there's only one class, so it's silly to meet after the test. I might come in just see if you have any general questions about the course, but otherwise we're done next Thursday. So I forgot what I was saying, kind of a roundabout thing. So tomorrow we'll mostly do examples, but we'll start one last thing. Monday we'll finish that last thing, and then Wednesday nothing but a questions view. Thursday test, which will be the last class. So any quick questions about this? No, I also should ready you for the fact that take-homes in general are a bit of a pain. So I would going to try to get it done by Monday, but don't count on it. Okay, so I'm going to stop recording, but stick around if you have questions.